Jump pass question 2001. Question number 37. Which of the following graphs correctly represents the variation of mass of a given material deposited with time for constant current in Faraday's law of electrolysis? This question is centered on Faraday's first law of electrolysis. As man look at the graphs, we'll be seeing the vertical and horizontal components, M and T. Okay, from the question also, you know this is Faraday's first law of electrolysis. Okay, let's start this way. What does the law say? The law says that M is proportional to Q. Okay, let me explain. See what Faraday's first law of electrolysis targets. Let me explain before I state the law. If I have water and I happen to be a doctor and I notice that my hospital has need for hydrogen and oxygen, I need hydrogen and oxygen. I need oxygen to feed to my patients, and I need hydrogen to power my plants. Okay, this is what I will do. I will get water. Then I will do electrolysis. What's electrolysis? When you get water in a reservoir, get metals or electrodes, immerse them in the water, then pass currents through the metals that has contact with water. Remember, the electrodes are immersed in water. Then put source of electrical energy to the water. What are you trying to do? We know that water is a compound, and the elements that make up water are hydrogen and oxygen. I want to break down the bond between these two, hydrogen and oxygen, making them to become one compound called water. Hydrogen, two hydrogen and one oxygen join together to make water. I have need for oxygen and hydrogen differently. Then I need to break down the force or the bond keeping them. So this is what we call extraction of elements. This is one of the tasks of electrolysis, to extract element from compound. So our question is centered on that. That's the first law of electrolysis. And Michael Faraday gave the world a beautiful idea how to extract elements from their compound. Michael says that to break energy, we need another energy. To break the atomic energy holding hydrogen and oxygen, we need electrical energy to break it down. And that electrical energy must be commensurate. It must be enough to break it down. And Michael now says that the mass of a substance deposited, the mass of oxygen I will liberate from the water compound or solution is directly proportional to the quantity of charge I will supply to the water. That's what the question is saying. That the more quantity of charge I supply to that water, the more mass of oxygen or hydrogen I will liberate or I will deposit in another reservoir. That's what I'm stating mathematically. That the mass deposited, the mass liberated is proportional to the quantity of charge supplied to the solution. If you want more oxygen from water, put more charges. Allow more quantity of charges to do what? To enter the water so as to break down the bond holding oxygen and hydrogen. Mathematically, mass is proportional. Mass liberated is proportional to quantity of what? Charge supplied to the solution. Then let's take it down. Then M is equal to, we take away the variation sign, KQ. KQ. Then recall Q is IT. Quantity of charge is current times time. Therefore, I can say mass is KIT. KIT. The K is constant. Then Faraday also made mention of that constant. Faraday called it electrochemical equivalent. Why? We're using electrical energy. We're using electrical energy to bring about chemical energy. Electricity, chemical equivalence. We use electricity to bring about chemical equivalence. So the name of this constant is M is equal to ZIT, where Z is electrochemical equivalence. Okay. Electrochemical equivalence. Then from this equation, we can now solve the equation. Then going back, we're giving graphs. See what the graphs are saying. Yeah. This graph is saying that the more the mass liberated, the more the time accumulated. You can see it from the formula. M increases with current and also increases with time. Put together, M increases with quantity of charge. So this is direct proportionality. Then we'll have that here. But there's an issue here. It didn't start from 0. Yeah, it didn't start from 0. It goes down to negative M. It goes down to negative M. We don't have negative M here. The mass liberated is positive. It's always positive. So that's what makes this one wrong. But the pattern above this negative axis is okay. But going down to negative Y component fouls this first graph. So this is wrong. Then coming to second one, let's see what this one is saying. Here is 0, the origin. So this is a bigger mass. So this one is saying a bigger mass goes for a smaller time. Then the smallest mass liberated goes for the longest time. This is inverse proportionality. So that's wrong. We are saying that the more mass liberated, the more quantity of charge, the more current, the more time. It takes a greater time, which implies that a greater quantity of charge has entered the solution to liberate the mass. So this one is saying the opposite, that it takes a very short time to liberate very big mass, and it takes a very big time or long time to now liberate a very tiny mass. So this is wrong. Okay, we'll fault this. So this has been faulted. Then coming here, let me move to D. D is also saying inverse proportion, but it's not a straight line graph. So it fails two ways. It's a curved graph, and also it's inverse proportion. A bigger mass for a shorter time. Then a smaller mass for a longer time. Big foul. Okay? Then the last one is the best option. Let's see what happens there. It starts from the origin. Small mass, little time. When the time begins to increase, we're liberating more mass. As the time is increasing, we're liberating more mass. More time, more mass. More quantity of charge, more time, more mass. So this is the best option. That is in accordance to Faraday's first law of electrolysis. Recall, the mass liberated in electrolytic cell, the mass liberated in electrolytic cell is proportional to the quantity of charge supplied to the electrolytes. And this quantity of charge is the same thing as current and time. That means higher time, higher current implies higher quantity of charge, and we'll have a greater mass liberated. Thank you. Stay tuned as we push ahead.